Hello everyone, this is ANUDEEP from ECE and I am going to discuss FIR filter design using frequency sampling method. Here we are given with an ideal frequency response of a digital FIR filter HD of e power j omega with period 2 pi. Now we will sample the given frequency response with n samples in frequency domain. And as we have sampled the frequency response, omega will be discrete and it will be replaced by 2 pi k by n, where k runs from 0 to n minus 1. And if we apply IDFT to the sampled frequency response, we can obtain the time domain representation of the filter with n samples. And this is the equation for the time domain representation of the filter, and n runs from 0 to n minus 1 as it will be having n samples. To make filter simple to design and practical, h of n should be real. For h of n to be real, all the terms in the summation should be real. But we cannot say all the terms in the summation will be real as we are multiplying e power j 2 pi k by n, which is a complex number with h of k, which may or may not be real. But for k equal to 0, the term will be h of 0 into 1, where if h of 0 will be real, we can get a real term. And we search for conjugate of h of k into e power j 2 pi k by n in the summation, so that when we add them, imaginary parts will be cancelled and real parts will be added. So if we apply conjugate for h of k into e power j 2 pi k by n, we get h star of k e power minus j 2 pi k by n. By circular shift property, we can write it as h star of k e power j 2 pi n into n minus k by n. Here, the exponential factor corresponds to n minus k term in the summation. So, if the coefficients of both the terms are equal, their imaginary parts will be cancelled, making the summation real. So, here h of n minus k should be equal to h star of k for k equal to 0 to n minus 1. By the analysis, after simplification, we get these equations for capital N equal to odd and capital N equal to even. With the obtained h of n, we can plot h of e power j omega and check the obtained frequency response of the filter. As we increase the value of capital N so that we can take more samples, the plot will be more close to the ideal plot. Now let's see an example. Design a filter having frequency response e power minus j 3 omega for omega 0 to pi by 2 and 0 for omega pi by 2 to pi. First, we sample the frequency response with n equal to 7, so that now omega will be 2 pi k by 7, where k will be 0 to 7 by 4. Replacing omega equal to 2 pi k by 7, we get this representation. Now here n equal to odd, so from the equation we derived, we get h of n equal to 1 by 7 into e power minus j 3 into 0 by 7 plus 2 into k equal to 1 to 3 real part of e power minus j 6 pi k by 7 into e power 2 pi k n by 7, where n runs from 0 to 6. By simplification, we get these equations, and real part of e power minus j 2 pi k into 3 pi n by 3 minus n by 7 will be cos 2 pi k into 3 minus n by 7. By expanding the summation, we get this equation. It is the required time domain representation of the filter of the given frequency response. Now we will see MATLAB code for design of FIR filter using frequency sampling method. Here we will take capital N equal to 50 and we will design a low pass filter. FIR2 is a function which returns an nth order FIR filter with frequency and magnitude characteristics specified in vectors f and m, and it will use frequency sampling method to design the filter. Here, for frequencies 0 and 0.5, magnitude is 1 and 1, and for frequencies more than 0.5, that means 0.21, the magnitude is 0 and 0. And we'll be passing these parameters to the FIR2 function and it will return an filter. Now we'll be plotting the frequency response of the filter, and let's see, for frequencies up to 0.5, the magnitude in dB is 0, that means the gain is 1, and after that the gain has fall down. This represents an low pass filter. And similarly, let's observe the characteristics for high pass and band pass filters. For high pass, For frequency 0 to 0.5, the magnitude is given as 0 and 0, and for frequencies greater than 0.5, the magnitude is given as 1 and 1 and 1. Here we can see the plot, and we are having a linear phase. And similarly for band pass, we are having a magnitude 1 for frequency 0.2 to 0.7, and for remaining frequencies the magnitude will be 0. Here we can observe the plot. Thank you.